For this video, we're going to be doing homework 2, part B. We're going to explain and implement Newton's method for finding the root of a vector and dimensional function. So basically, we're going to be using a system of equations of k variables and k functions. You want to be able to use Newton's method to solve systems of k equation, which amounts to finding the simultaneous zeros of k continuously differentiable functions. This is equivalent to finding the zeros of a single vector-valued function. So basically, we're going to have our new guess is equal to our old guess minus the Jacobian of the old guess, the inverse of that, and the function of the old guess. So we're going to be making a system of equations. We're going to be putting it into a matrix. We're going to get a Newton's functions that returns the root of two roots, and we're going to be using an imported function to find those roots, but we're going to be creating the Newton function for looking for it. So basically, what we're going to need to do is we're going to define Newton. We want Newton's functions with multiple functions. We want our final guess, the initial guess. Max iteration is going to be 100, and that's just going to allow us to not keep running on for so many times. So we're going to have a limit to it so it doesn't crash and doesn't go on forever. Our tolerance, we're going to be putting at a very low level. Now we want to find the Jacobian of f. To do that, we already have a built-in Jacobian function to look for that. And f of 0, we're going to put that into the initial old guess. And then we want to iterate through this. Max iteration. We already said what it was 100. It's going to go and stop when it finds that value. And that equation that we had to solve system of equations, we're going to be taking the inverse of that, and we're going to be finding the Jacobian of that as well. And we're going to do that all at f of 0. Oops. And then we're going to need to do the function of 1 with the first element, second element. Then we're going to need it to break when it finds that the function 1 is less than the tolerance. So it's going to use linear algebra to be able to do this. And then it's going to break. Now we're going to say x0 is equal to x1. f0 is equal to f1. And we're going to want to return x of 1. Okay, let's clean this out, make it look a little more clean. So now we have we want to find the root. So we have two nonlinear equations. We got a nonlinear equation. We're going to implement that, but we want to turn this into an array. And then we want to also be able to put this array and define its initial values. And since it's going to be a Boolean, we need to implement that. We're going to define our Newton function. and then we're going to say f is equal to fun, that fun function that we found online. Oh. And then we found our two values for the roots of a vector, n-dimensional function.